Hello and good morning everyone. Your physics exam is today and I am here with 30-minute revision, so you can score at least 50 plus marks. So watch this 30-minute revision video. Here I am going to quickly discuss all the important questions that might come in your pre-board. Right? Let us start. We do not have too much time. We have to finish this within 30 minutes. So first question that might come is state and explain Coulomb's law or Coulomb's law in vector form. Remember, the answer is same. Only thing is the difference in this form where you have to write the equation in vector form and draw a diagram like this. Okay, that is the only difference. And what you have to write? You have to write Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. It acts along the line joining the charges, right? And mathematically F is equal to 1 by 4 pi epsilon naught q1 q2 by r square r cap. Okay, and if you only vector form is asked, you can skip the test statement. Only you have to draw the diagram clearly, neatly, and write this equation. And also the expression has to be all the variables that you are using has to be mentioned clearly in this equation. Now next question, write any three properties of electric charge. Very important question. Additivity of charges. Charges are additive in nature. Quantization of charges. All charges are integral multiple of smallest charge, small e. Conservation of charges. Total charge in an isolated system is conserved. Next, write three properties of electric field lines. Electric field lines may start from positive charge and end at a negative charge. Okay, clear? Two electric field lines are never intersected each other. Electrostatic field lines do not form any closed loops. In case of magnetic field lines, there are small difference that it starts at positive north pole and ends at south pole, but inside the magnet it goes in the opposite direction. Okay, and they form closed loop. Okay, so that is a small difference. Question number 4, on what factor does the capacitance of a parallel plate capacitor depends? C equals to A epsilon naught by D. You have to write a K as well. Okay, and you have to mention that directly proportional to the area. So C is directly proportional to area, inversely proportional to the distance between the plates, small d, and directly proportional to the dielectric constant between the plates. Okay, so if this is a capacitor, in between the capacitor we have a dielectric medium, the width, the distance between them is d, the area of the plate is A. Okay, next, write two properties of equipotential surface. No work is done in moving a test charge over an equipotential surface. Electric field is always normal to the equipotential surface at every point. No two equipotential surfaces can intersect each other. So this is very important and easy to remember as well. Next, mention two limitations of Ohm's law. Very important. Ohm's law is applicable only if all the physical conditions remain same. Ohm's law is not applicable at very low and at very high temperatures. Ohm's law is not applicable to non-ohmic conductors, for example semiconductors, discharge tube, etc. Next is state and explain Biot-Savart's law. Write its vector form. Okay, so this is the expression for the diagram is compulsory when you are writing the Biot-Savart's law. It is directly proportional to strength of the current I, directly proportional to the length of the current element dl, directly proportional to the sine of the angle between the current element and the line joining the given point of charge and midpoint of the current element, and inversely proportional to the square of the distance between the current element and the point. Now if they ask you about the vector form, you have to write dB equals to mu naught by 4 pi I dl cross r cap. Remember r cap divided by r square. If you are using r vector over here, it will be r cube. So don't mess it up. If you remember r cap over here, that will be very easier for you. So I dl cross r cap divided by r square. This is same as or almost same as its scalar form. Only thing is in scalar form there was a sine theta. So in vector form sine theta is missing obviously, and dl cross r cap. Okay, so remember this. So this will help you to answer the question. Next, what is Lorentz force? Write the expression and explain the terms. Force acting on a moving charge particle in the presence of electric field and magnetic field is called Lorentz force. F is equal to Q into E plus Q into V cross B. So expression is very, very essential. You also have to explain what is this. F is force, Q is charge, E is electric field, V is velocity of the charge, and B is magnetic field, right? Next is, how can a galvanometer be converted into a voltmeter? Explain with the diagram. So this is a very, very important question, super important question. So do not skip this question. A voltmeter should have a very high resistance because it is connected in parallel in a circuit. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with it. This way, the overall resistance of the voltmeter remains very high. So V is equal to G plus R into I. And the diagram is this. You have to draw this diagram. Without the diagram, you are not going to get marks. Next, another important question: how can you convert a galvanometer into an ammeter? Okay, explain with diagram. An ammeter should have a very low resistance as it is connected in series in the circuit. This is achieved by connecting a suitable low resistance S in parallel called shunt with a galvanometer. This way, the overall resistance of the ammeter remains low and the galvanometer is converted into an ammeter. The expression for current in an ammeter is given by I equals to G plus S divided by S into IG. IG is the galvanometer current. The diagram is drawn like this. So this is the diagram. You have to draw this diagram G and S. Okay, don't skip the diagram. Also, the expression is also very, very important. These two questions are super important. Next is, write three differences between diamagnetic, paramagnetic, ferromagnetic substances. Any two of them will come, and how to remember it? So you have to remember the properties and respected answers. Okay, for example, for magnetic behavior, diamagnetics are weakly repelled, paramagnetic are weakly attracted, ferromagnetic are strongly attracted. Now what about magnetic susceptibility? Have a small negative susceptibility, have a small but positive susceptibility, have a very large susceptibility. What about effect of magnetic field? When it kept in external magnetic field, the field lines are repelled weakly, the field lines are attracted weakly, the field lines are attracted strongly. Okay, so the magnetic moment in the same direction as the applied field. Okay, strong magnetic moment. Now next is, derive the expression for motional EMF induced in a straight conductor moving perpendicular to the uniform magnetic field. So let's see. So first of all, the diagram is compulsory, this kind of diagram. Here this cross represents the magnetic field into the paper. So that magnetic field is given by B. Okay, the length is given by L and the width is given by X. Now what is the flux linked with this coil at this particular time? The flux linked with anything is given by magnetic field into area. Okay, so here it is a rectangular surface. So rectangular surface means what is the area? Area is very simple, B into L into X. This is the area. So you can say the flux linked is B L X. Now from Lenz's law, what is induced EMF? Lenz and Maxwell's law, Lenz and Faraday's law combined. So induced EMF is given by minus d phi dx. Okay, so minus d phi dx. So you have to differentiate it, and at this point the differentiation is very easy. B and L are constant, so they will be common, and you will get d phi by dt, not dx. Okay, d phi by dt. Dy, rate of change of flux with respect to time. Now B, L, N are constant, but x is changing. Y, x is changing. Let us understand that. So as you can see that the rod which is kept like this, it is moving in this direction. So that means this x is slowly decreasing. So when the rod is over here, the x value decreases. When the rod is over here, the x value decreases further. That means x is changing with time. Now how it is changing? As you are coming closer and closer, the area is decreasing. So we can say that the velocity of the rod can be given by minus dx into dt. Okay, velocity of the rod is minus dx by dt. Why minus? Because as it is moving towards the other end, okay, the area is decreasing. So to represent that, the velocity has to be minus. So we get that BL V. So induced EMF is VLV. Don't forget the minus sign and don't forget the minus sign in V either. The actual result is positive, so don't make a mistake over here. Very simple, easy derivation. Draw the diagram, explain a little bit what is length, what is width of this wire, what is area, and then start with the derivation. Okay, next, write 3 features or properties of nuclear force. Very common question. The nuclear force is much stronger than Coulomb force acting between the charges or the gravitational force between them. The nuclear force between 2 nucleons falls rapidly to 0 as their distance is more than a few femtometers. The nuclear force between neutron-neutron, proton-neutron and proton-proton is approximately the same. The nuclear force does not depend on the electric charge, right? Now give Einstein's explanation of photoelectric effect and write Einstein's photoelectric equation. Einstein suggested that each photon of light has energy proportional to frequency nu given by E is equal to h nu, where h is Planck's constant. When light shines on a metal surface, photons transfer their energy into the electrons of the metal. Any energy from the photon exceeding the work function becomes the kinetic energy of the ejected electron. You can write the kinetic energy, maximum kinetic energy is given by E minus phi. That is the basic form of Einstein's photoelectric equation. Okay, you can write the other form as well. EV naught equals to h nu minus phi. That is also perfect. Any one of them is okay. Next, what is an intrinsic and extrinsic semiconductors? Intrinsic semiconductor are pure semiconductors, are called intrinsic semiconductors. The presence of charge carriers, electron and holes, is an intrinsic property of the material, and these are obtained as result of thermal excitation. Extrinsic semiconductor, the number of charge carriers can be charged by doping of a suitable impurity in pure semiconductors. Such semiconductors are known as extrinsic semiconductors. These are of 2 types, N-type and P-type. Okay, so clear. Next, derive an expression for electric potential at a point due to a point source charge. So we have a point source charge, say capital Q, and also this might accompany with the definition of electric potential, so that you have to prepare as well. What is electric potential? The work done to bring a unit positive test charge from infinity to a point in electric field is the potential of that point. Okay, so that is the definition. So here we are trying to find the electric potential, say at a point small r on the source charge capital Q. So this is the point small r, this is the point P, and this is an extended version, and we have to bring the charge from infinity. Now infinity is beyond our control, so we cannot go till infinity. So what we will be doing, we will be taking some intermediate point and we will be saying this is A, this is B, the distance between A and B is dx, and the distance is very small. Dx is very, very small. Why so? So that the electric force is almost constant. Now electric force is varying with distance, right? Coulomb's force. Suppose you have a unit positive test charge. I have done this derivation multiple times in a different way. Today I am doing the shortcut way. So you have to take a unit positive test charge which started at infinity. The unit positive charge not started here, it started at infinity and it arrived at a point A. Okay, at this point A, what is the electrostatic force that is acting on it? The electrostatic force is given by, this is the electrostatic force. It is given by K Q1 into Q2 divided by R squared. The distance between source charge and A is x, so x square. Okay, this is a different point, right? And as the distance changes, the force will also change. So we have taken the distance between the Q and A as x. So this is x. Okay, now so this is the force, static force. Now if you want to move a charge, you have to apply a force which is equal but opposite to this static force. So the external force that you have to apply, the external force, that should be minus of kq by x square, right? This is the force that is must be applied to move this charge in the opposite direction, because the force is acting on the this side. So the static force is acting in this side, and you have to apply an external force to move it in the other side. Okay, so this is how you should consider. So the external force must be negative to that of the static electric force. Now work done, what is the work done to move the charge by a small distance dx? The small work done is given by the external force times displacement, right? This is the definition of work done that we learned in our PU1. Now, so what is the complete work done? To find the complete work done, we have to start at infinity and reach at this point, which is at a distance r, okay, and integrate this small work done. Then we can get the complete work done, and this complete work done is actually the electric potential, because we have taken the test charge as 1. Okay, so now the integration part is the only thing that you have to do. So electric potential V is equals to integration infinity to R. Okay, now we will put the value of dW, which is this. So F external, what is F external? F external is this. So minus KQ by x square into dx, right? So the dx is there. So this is the potential. Now V equals to minus, you can take common, K and Q you can take common. Only thing you cannot take common is this. So infinity to R dx by x square. Don't forget the negative sign, by the way. Okay, negative sign is very, very important. So dx by x square is what? And these two forces has to be mentioned: static force, external, internal force, and external force that you are applying. Okay, otherwise marks will be deducted. So now if you integrate this, what you will get? Minus kq, okay, and you will get minus 1 by x infinity to r. Now this minus can be taken common, and you can say kq 1 by x infinity to r, right? It is common for both of them, so it can be taken out. Now what is this? This is a definite integration. So V equals to kq into 1 by r minus 1 by infinity, right? So we have to put the upper limit first, next lower limit. Okay, so lower limit was infinity, so 1 by infinity is 0. So we get this as kq by r. Now don't leave it over here, give it a proper look. 1 by 4 pi epsilon naught q by r. Okay, so you have to put k is equal to 1 by 4 pi epsilon naught. So this is the derivation, very easy and most common derivation for your pre-board. Now next, arrive at the balanced condition of Wheatstone bridge using Kirchhoff's rules. So here we have the Wheatstone bridge. Again, I am going to do the shortcut method for this as well. So first you have to draw the diagram. Diagram is compulsory. Without diagram you will not get any marks, and when you are drawing the diagram you have to show the battery as well. Do not just show the 4 resistors without battery. This does not make any sense. P, Q, R, S. Okay, suppose current I1 is passing through over here, current I2 is passing over here, then I3 is over here and I4 over here. The current through the galvanometer is Ig. Okay, now what is the balanced condition? Balanced condition, in balanced condition, okay, Ig should be equals to 0. Okay, in balanced condition Ig should be equals to 0. So what we can say? Therefore we can say that I1 is actually equals to I3 and I2 should be equals to I4, right? So if Ig is 0, if this current is 0, then this current should be equals to this current from Kirchhoff's laws. Okay, again I2 should be equals to I4 as well. Okay, so these two currents must be same because Ig is 0. Now what? Now we have to apply Kirchhoff's voltage law in this loop A, B, C, D. Okay, so this is the square. So we have to apply, first we will apply A, B, D, A. Okay, applying Kirchhoff's law, applying KVL, Kirchhoff's voltage law, or you can say Kirchhoff's loop rule. Okay, at A, B, D, A. Okay, ABDA means ABDA. Starting point and ending point should be same whenever you are writing a loop. Okay, applying KVL at ABDA, what we can say, I1 into P plus 0, this is 0, and minus I2 into R. And from here we can say that P by R equals to I2 by I1. Okay, so now you can write similarly, applying KVL at BCDB, we can write Q by S. Okay, now if you see that P by R is I2 by I1. So what is the current through P? P is I1, but it is coming in division, right? So Q, what is the current through Q? Current through Q is I3, so it will be in the division, and current through S is I4, that will come in top portion. So it is an inverse, P I1, R I2. Similarly, Q is I3, S is I4. Now we also know that I1 equals to I3, so we can write this as an I4 equals to I2, so I2 by I1. Okay, so if you see that equation number 1 and equation number 2 both are same, right hand side are same, so comparing these two we can write P by R equals to Q by S, or P upon Q equals to R upon S. This is the balanced condition for Wheatstone bridge. Very easy, very small, very simple. Next, derive the expression for magnetic field at the point on the axis of a circular current loop. Now remember, all the questions that I am discussing here are probable. Exactly the same question might not come, so I have done all the important detailed derivations, so do check that out if you get time. Otherwise this is just a last minute preparation, and all the questions are definitely very, very important. So here we have a circular loop of radius r, and we are trying to find magnetic field, say at a point P at a distance x from the center. Okay, so here let us take a small point, and also remember the angle here is 90 degrees. Also the effective magnetic field is this, but we will only get the magnetic field along the x direction. Why so? Because y direction will be cancelled. So if you consider another element over here, the element due to this will be in this direction, and the y direction there will be no net magnetic field. Magnetic field will only be along the x direction. This is x axis, right? Now, so if this is capital R, this is small x, this is small r, given by root over r square plus x square. Now what? Now what you have to do, you have to combine them quickly and find the dbx. So this is dbx, this is dbx. Now what? So we will apply Biot-Savart's law, and also this angle is given by phi, this will be phi, so dbx equals to db cos phi. Okay, now what is dB, by the way, from Biot-Savart's law? Mu naught by 4 pi I dl sin theta by r square. Now, sir, where is sin theta? Sin theta is gone because sin 90 is 1. So this theta, whatever angle we are taking, this is because this is perpendicular to the tangent, the angle will be 90 degrees, so sin 90 is 1. But we will have a cos phi over here. This cos phi is coming from here. Okay, now let's put the values. So mu naught by 4 pi I dl by r square. Now what is the value of cos phi? So if you see that this is phi. Okay, so this is r and this is hypotenuse small r, so it will be capital R by small r. Okay, base by hypotenuse, so we get mu naught by 4 pi I dl r by r cube. Now this is small magnetic field. So whenever we see small, what do you have to do to find the complete? We have to integrate it, right? So dBx complete. Now here our starting point and ending point are same, that's why this is a closed integral. Now in case of closed integral, what happens is that obviously mu naught by 4 pi is constant. Again I r by small r cube are constant. So we only get closed integral of dl. dl is this element, right, the element that you have taken. Now if you add all the such elements, you will get the circumference of the circle. So you can write mu naught by 4 pi ir by r cube into 2 pi capital R. Okay, because this is circle, so radius is capital R. So 4 pi 2 pi cancels and you get this as mu naught by 2 ir square by small r cube. At the last step, what you have to do, you have to write the value of small r cube. So bx equals to mu naught by 2 ir square divided by r square plus x square to the power 3 by 2. Okay, r is actually half of this value to the power half, and here we have a cube, so that's why it is a 3 by 2 in the power. Okay, so this is a very easy derivation. Again, practice it and you should be able to answer. Now next, most common question that might come in your pre-board: what is a rectifier? Explain the working of a full wave rectifier. Using the neat circuit diagram, draw its input output diagram. A rectifier is an electric device that converts alternating current into direct current. Positive cycle to AC input. During the positive cycle of the AC input voltage, the upper half of the transformer secondary windings becomes positive. Diode D1 becomes forward biased and conducts, allowing the current to flow through the load resistor. RL, diode D2 is reverse biased and does not conduct. So this is the diagram that you have to remember, and you have to draw this input output diagram. Only one is sufficient. During the negative half cycle of the AC input voltage, the lower half of the transformer secondary windings becomes positive. Diode D2 becomes forward biased and conducts, while diode D1 is reverse biased and does not conduct. Current again flows through the load resistor RL in the same direction as during the positive half cycle. Okay, what is a half wave rectifier? Again, same question. A half wave rectifier is an electronic circuit that converts alternating current AC into direct current DC by allowing the current to flow only during one half cycle of the AC input signal. The other half cycle is blocked. Okay, so that's why it is called half wave rectifier. The diagram is very simple. Don't confuse between the diagram of half wave and full wave. Now working during the positive half cycle of the AC input, the P side of the diode is positive with respect to the N side. The diode becomes forward biased and conducts current. Current flows through the load resistor RL in one direction and voltage across the load is positive. During the negative half cycle of the AC input cycle, the P side of the diode becomes negative with respect to the N side. The diode is reverse biased and does not conduct, so the current flows to the load resistor is 0 and the output voltage is 0 during this half cycle. So if you see the input output diagram, so during the input output diagram only the half cycle is converted. Okay, so this is the end of this lecture. If you have any doubts, please don't forget to mention in the comment section below. Also, if you want the PDF of this, then don't forget to come to our WhatsApp channel. The PDF will be shared there. Thank you.